All right, something that's going to be important about this backside as we're taking roots is that now we're working with an expression, not equations. So expressions means there's no equal sign. And if you look through kind of on these pages, no equal signs anywhere, which means we're going to drop the plus or minus. That's only when we're working with equations. So the reason this makes people mad, especially coming into the final, because if you're working with an expression, you don't want the plus or minus, and you're actually now wrong if you put the plus or minus, which just gives people fits, because it used to be if you didn't have it, you lost points. Now if you do have it, you lose points. So equations use plus or minus. Expressions don't. All right, so some vocabulary here for us. Something called the index. It tells us what root we're working with, whether that's square root, cube root, fourth root, all that stuff. You'll always get to see your radical sign. And then you'll have this guy here called the radicand. All right. For some reason, it always reminds me of Toucan Sam, the Fruit Loop guy. It's radicand. All right, so here's what we're going to be doing a lot of in this chapter, is simplifying different types of roots, some of which just have numbers, some of them have numbers and variables in it. It's not going to start off very complicated at all, and then it kind of builds up as we go. But if you understand the smaller pieces, it's just not that hard. All right, so all these here are going to be perfect fits with their roots. Eventually, we'll get into, because we did some in earlier chapters, like square root of 20, where we'd break it up into 4 and 5, square root the 4 to get 2 square root of 5. Eventually, we'll do this concept with cube roots too, like we'll have 54, and we'll split it up into perfect cube roots. We'll do a little bit of that later on in this chapter. But these here are all going to fit perfectly. And you'll start to get more and more familiar. Hopefully now we've come to terms with the cube root of 27 is 3. This is a negative 27, so this would be a negative 3. I know I don't have any equal signs flying around here. We're just simplifying, so just changing it forms for us. We should be very comfortable with square root of 16 being 4. Key concept, though, not plus or minus, because we're working with an expression, not an equation. Okay. So here we've got our fourth root of negative 64. All right, so this one, actually isn't a perfect fourth root. It would keep going. Here's how we can go about doing this, though. All right, so we'll kind of get to experience this, and we'll get lots of practice with these as we go. So it does have a decimal answer, but we're basically going to look for this in terms of, can I find a perfect fourth root in there? So a couple ways of doing this. So let's kind of jump in on this one. Let's come up with now 64, we could call this 8 and 8. You could also do 32 and 2, 16 and 4. There's lots of ways to start this off. I was going to pick 8 and 8. Now, this 4 is telling us that I need a group of 4 things to escape. Oh, no, okay, I remember now. We actually don't need to do any of this. This is negative here, which means this is going to have no real answer because it's a negative to an even power. But just for fun, since we've already started here, let's pretend for a minute that this was the fourth root of a positive 64. Here's how we would do it. This will be a nice little intro to what we'll be doing later on. So I broke it down into 8 and 8. All right. So then I need to find a group of 4 things, which I don't have yet. So I could break this down to 4 and 2. I could break this down to 4 and 2. And then break the 4 down into 2 and 2. Okay. So then we'll be left over with all these guys, everybody kind of at the end of the branches. So what we do is, since this root out here is the fourth root, we need to take a group of 4 2s. So here's 4 2s. And that 2 is going to escape. What's left over is a 2 times 2, which would be a 4. So this would be 2 fourth root of 4. All right, and we'll get into more of that later on in the chapter. Now this is the exact same process that we actually used to do up here when we did square root of 20. This 4 was really a 2 times 2. Our index here was 2. We took pairs of 2's and took it out to get that 2 and left the 5. So it's the same process, but it gets more complicated when our index is larger because it takes more to escape. It takes that number to escape. All right, but to answer this original one, this would be no real answer. Okay. All right, so on this one here, this is just kind of showing us that if there's a negative underneath, don't automatically come to the conclusion that we can't do it, because this one would get fixed when we square that negative force. This is really just saying square root of 16, which is a 4. So we can sometimes need to simplify what's underneath before we move forward. All right? Now sometimes there'll be an exception on this that we'll kind of work with. It's more complicated when we're working with even roots. Now this index is 2. It's invisible, but that's a square root there. Now, if you're working with even powers, you really need to simplify first to get rid of that negative. When we're working with odd powers, though, negatives are fine. So what we'll also kind of learn to do is recognize that this 3 and this 3 will essentially just cancel out, making our answer here -3. You could you could do -3 to the third power, which would give us a -27, and then cube root it. It's going to take you back to that same answer. So we can kind of shortcut it with odd powers. Can't shortcut it with even powers, though, because if you try that on this one, to cancel that and cancel out, you get an answer of -4, which doesn't make any sense because you can't get a negative answer out of a even root. So just a little semantics there. Basically, even roots are a little bit harder to work with. Okay, so some of these down here will look intimidating. They're actually not that hard at all, and they'll pick up in intensity, but here's what happens. You just take it piece by piece. So the cube root of 27 is a 3. So 3 is going to make it on out here. Now let's visualize this y as being 1, 2, 3, 4, 5, 6. And we're looking for groups of 3 to escape. So this group of 3 can escape and become a y on the outside. This group of 3 can escape and become a y on the outside. So on this one, actually, everybody on the inside of the radical sign is going to make it out. Now, 3y, we wouldn't leave our answer like that. That would be a 3y squared, because y times y is y squared. All right. So, shortcut here is basically we'll be taking our inside exponents, dividing it by our exponent. 6 divided by 3 gave us this 2 there. All right. Here we've got fifth root. You'll get more comfortable with your powers of 2's. 32 is the fifth root of for 2. And then we have y to the 10th. So you could either draw out the picture, circle groups of 5, or just think of this as being 10 divided by 5 to get y squared. Everybody made it out here again. All right. So it looks like it's all complicated at first, but it's really not that big of a deal. Numbers are way more difficult to deal with than exponents and variables, because we actually have to know different powers, or later be able to draw that tree diagram like I showed above to find the missing pieces that get to escape and some that get to stay. All right. So this one, if you don't see an index, it's just square root. So square root of 16 is 4. You could draw out 8a, circle groups of 2, you'd get 4 of them, or just do 8 divided by the 2 to get 8 to the 4th. All right, so there's that. So as you can see, these also are pretty easy and only take about 2 to 3 seconds. Okay, so this one has no numbers. No numbers is good news, makes it even easier. 6 divided by 3, 9 divided by 3. Remember, if you ever get confused on these, just draw out the pictures and circle your groups of 3s. All right, so another one with no numbers, nice and easy. X to the first power, you don't have to write the first power. Y cubed. All right, not too much to it. Now in this one, we'll get to see the concept of remainders, some stuff getting left behind. So you just go one piece at a time. Cube root of negative 64 is a negative 4. Because cube root of positive 64 is positive 4. And then let's take a look at our x's. I've got 3 of them. Takes 3 to escape. So 1 makes it out. Now here's something new for us. This is y to the 7th. If you do, 7 divided by 3, obviously you get a decimal. So here's really what's going on. We've got 1, 2, 3, 4, 5, 6, and 7. This group of 3 can make it out. This group of 3 can make it out. So I'd have a y and a y, giving us y squared. But still left within this cube root is this y right here. You didn't make it out. So if it doesn't match up perfectly, basically, hey, I could divide it out 3. I could divide this 3 out twice to get that y squared, and there would be 1 y left over. Similar concept here with the z. I've got our 10 divided by 3. I could do that 3 times, and there would be 1 left over. And then there would be our answer, and it's perfectly fine to have stuff left over. Now, things that people mess up on is they get excited and forget to say that this is a cube root, right? It started as a cube root. It's going to finish as a cube root. I need to put that there. That exponent's different than this, so nobody's sharing exponents. Everybody gets their own. Might be an invisible 1, but everybody gets their own exponent. And that is about it for that.